Hi everyone. So let's go ahead and continue on with our section 5. And last thing that we were talking about was blood pressure. Now we're going to be taking a look at this other factor that influences blood flow, which is going to be resistance. So resistance is not good for blood flow. Look at that. It opposes total blood flow. Because what it is, it's going to be any kind of friction that blood experiences when it's traveling through the wall. So it's usually because it's going in and hitting the blood vessel wall more often, or it's going in and all of the little substances in the blood are running into each other because it's a little crowded. So that's what resistance is, specifically peripheral resistance. That's what we're going to be taking a look at, is this resistance of blood in the blood vessels. Remember, we talked about resistance in the heart. We talked about afterload. So this peripheral resistance is specifically looking at blood vessels. We're going to take a look at, there's three things that are going to affect resistance: viscosity, length, and lumen size. So let's go ahead and start with viscosity. Viscosity we've already introduced, right? It is basically the thickness of the blood and how the resistance of fluid to its flow as well. So the greater the thickness, the greater the viscosity, and that means that if you have something that has high viscosity, that is going to increase resistance. And what that does is it is going to slow flow down. I like to think of this as when you are drinking a milkshake, right? So drinking a milkshake as opposed to a soda. So let's say that you go to, I don't know, wherever you like to get milkshakes, and your significant other orders a Dr. Pepper, and you order a chocolate milkshake. If you think about which one's going to be thicker, it's the milkshake. So that is going to oppose flow, right? It's a lot harder to get a milkshake through a straw than it is a Dr. Pepper. And it has to do with the thickness. It has to do with how many things are floating around in that bloodstream. If you have thicker blood, that means you have a lot more maybe red blood cells that are floating around. So they run into each other more often. They run into white blood cells more often. They run into the wall more often. So that creates resistance. And that is going to decrease blood flow. So always think about viscosity and what it has to do with blood flow and resistance. Link it back to your milkshake versus your Dr. Pepper, right? So anytime that viscosity changes, it's going to definitely change resistance, which is going to change blood flow. So do you see how these are going to be? Let me see. It will not let me write an arrow. Come on. There we go. Blood flow and resistance are going to be inversely related. So when you have something that's not as viscous, if you decrease the viscosity, then that is going to go in and decrease resistance, which is going to help increase blood flow, right? Your Dr. Pepper, your soda, or water, whichever one you prefer to drink. So that's how viscosity is going to influence everything. This usually doesn't change in our body. Viscosity is usually constant, right? Blood viscosity is usually constant, unless we go to high altitude where it can change, unless an individual is blood doping, unless an individual is anemic, that's when it's going to change viscosity. So if you think about with blood doping, I just mentioned, or high altitude for a long period of time, it is going to cause your blood to get thicker, which increases resistance, which decreases blood flow. And we'll talk about how when this happens, the heart has to work harder to pump your blood through the vasculature. So we'll look at that at the very end when we put pressure in with this. All right, let's take a look at length. This is another one of those that don't really change at all throughout our lifetime. Yeah, whenever you're young, it's going to definitely change. Because your vessel length does increase, but when you reach adulthood, it doesn't. Another time that vessel length could increase is through weight gain. So let's think about it. Let's go back to drinking our soda or drinking our water through a straw. You want to have just a normal straw so you can, of course, be able to get that drink into your mouth as quickly as possible. But what happens when you put one of those crazy, weird, long, twisty straws into your drink and you try and drink through it? It takes a little bit longer for the drink to get through the twisty straw to get into your mouth. So anytime that you increase vessel length, look at that, you are going to increase resistance. And remember, anytime that you increase resistance, you decrease blood flow. So again, we're going to talk about how sometimes pressure comes into play to make sure that blood flow stays where we need it to. So we're going to put all three of them together later on. So shorter vessels, less resistance, that's what you want. Longer vessels have more resistance, and that's not what you want. Now let's take a look at the one that will change, and it even changes throughout the day because it's going in and trying to meet the needs of the body, and this is vessel radius. This is going to be one of the key things that the cardiovascular center is going to go in and regulate and change to help regulate blood pressure and blood flow. So a smaller radius, if you think about it, here's one radius, and then there's a bigger radius. You can get a whole lot more blood through this big giant radius than you can with a small radius. So smaller radius is going to create more resistance, and that is going to decrease your blood flow. And we just talked about that with local blood flow, how whenever the precapillary sphincters contract, that's going to decrease blood flow into the capillaries. Whenever they relax, it's going to increase blood flow through the capillaries. That's what's happening here. So it's just talking about how blood is laminar. So if I went in and kind of drew a longwise picture of my blood vessel, this laminar flow means that the flow rate is different. It's fastest in the center, but it's going to be a lot slower up against the blood vessel wall right here, much slower up against the blood vessel wall. So that's why if you have a lot larger vessel, it is going to give it more room in the middle to flow through it. So as diameter increases, like through vasodilation, less blood is near the edges. It can flow through the center, less resistance, increase of blood flow, which is great. So again, we have to go back and link and relate this to our drinks, right? Very important. So think about if you like boba tea. When you get boba tea, there are those little things in there, and you need to have one of those big straws, right? If you don't have a big straw, if they give you one of these small straws, you're not going to be able to drink. You'll be able to drink some of it, but eventually you're not going to be able to get your little bobas through. So that's why you want one of those big giant straws. It's kind of like going back with a milkshake too, right? Whenever you go to to get your milkshake, it would be so much easier if you had a straw that they use for boba and not one of those normal regular straws that they use for soda. Because whenever they give you those really small straws, you have to really, really kind of suck really hard in order to get that milkshake through your straw. So that's why it's important to have a nice open blood vessel like that. So this is just kind of going in and talking about the relationship between blood flow and the radius. Look at that, flow proportional to the radius to the fourth power. I'm sure you're thinking, what are you talking about? So that's saying that if I have one radius, that's 1 millimeter, but then I have another one, the radius is 2 millimeters, then that means that the change in flow in this one is 16 times greater than this one. So that's what that whole R to the fourth power means. So again, this resistance is going to be regulated by the arterioles. We'll look at this in the next section whenever we look at regulation of blood vessels with vasodilation and vasoconstriction and how it's going to be from that sympathetic division of the autonomic nervous system. Another thing that can change resistance is anything really that changes the lumen size of your blood vessel. So if you do have one of these nice open, right now it's open blood vessel, but you start to get atherosclerosis, look what's happening to my lumen. It's getting smaller and smaller. So that is going to go in and increase my resistance. And obviously it's going to decrease my blood flow because I don't have as much room for it to flow through. So that's another thing that can go in and change resistance along with vasoconstriction and vasodilation.